So for these equations of motion, we're talking about constant acceleration. Just think about what that means for a second, what we're talking about here. So in the previous problems, we just had constant velocity. And so in the case of this wee online app, essentially the car's just moving along at constant speed. Let me just run that again. Let me reset it. And so this is the gas pedal apparently. So this is your accelerator pedal. I'm just quickly clicking that so we're not accelerating too much. And so just click that and the car's moving along at constant speed. So that's when you can use these equations, S at time t is equal to S naught plus velocity times time. It works for when that car's moving at constant velocity. So the speed of the car is not changing, or the velocity of the car is not changing if you're looking at velocity. Now, what we're looking at now is we're looking at situations of constant acceleration, which includes this one. In this case, speed's not changing, acceleration 0. It does have constant acceleration. It's just that acceleration is 0. But the other types of problem we're going to get now is where we've got constant acceleration. So I've set the acceleration at 2.5 meters per second. We've got some initial speed. So the car's starting with a speed. Let's just up that a little bit. Let's start him at maybe not too fast. Let's start at 10 meters per second. And so we're just going to hold the gas this time. And so that car is accelerating now. That's the type of problem we're talking about now. So we've got objects where the speed of the object is changing as time passes. So that's a reasonably low acceleration. Let me just reset. So let's just up the acceleration a little bit. And we've reset everything. So this time we've got a higher acceleration. You can see that speed's increasing more quickly. So that's the type of problem we're talking about here. Could be increasing, that's acceleration, or the speed could be reducing, that would be deceleration. So just keep a clear idea of what we're doing in each of these sections. Previous section, we're looking at constant speed. That's like you're not pressing the accelerator. This section, we're looking at constant acceleration. That includes constant speed. It's just an acceleration of 0. But it also covers other situations where things are speeding up. So for this first example here, we're looking at a rocket. A nice first step in these problems until you get used to them is just to quickly write down the equations of motion for an object that has constant acceleration. So the displacement at time t is just equal to the initial displacement plus the initial velocity times time plus half times the acceleration times time. So let's have a look through what we've got here. So this is initial, this S naught is initial displacement. That displacement will be changing as time passes. This is the initial displacement. This is the initial velocity. So the velocity at time 0 is V naught. Now A naught can be the acceleration at time 0, but it's also the acceleration at any time for this stage of the motion. So it might be different stages like the pool ball we had where the equations change at different points in time. But for this stage, that A naught, it's the initial velocity, but it's also the velocity at any time during that stage because it's constant velocity. We're looking at problems with constant velocity. Now, the other thing you can see there is that if this was 0, so say the acceleration was equal to 0, let me just write it out. So if A naught is equal to 0, then what you would find is this term here would just disappear and you would be left with S naught plus V naught t, which is exactly the equation we had for constant velocity. And so these equations also cover constant velocity if you just put in A naught equals 0. So that was that one. What other equations do we have? We also have, there's another equation, and we should, if we had more time, we would derive these, but we don't really have time. So I'm just introducing these equations to you. And so what you'd find is the velocity at time t squared, and often the way we write that, just so we don't have to do the brackets, is v squared of t. So the velocity squared at time t is equal to v naught squared. So the velocity at time 0 squared plus 2 times the constant acceleration that we've got times S minus S naught. Let me just double check that. It's been a long time since I've looked at these. So let's just double check that we've got that right. Oops, excuse me, just trying to grab it down. And so we've got, oh, we'll come back to that one. So displacement is equal to, so the velocity at time t squared is equal to v naught squared plus 2a naught s minus s naught. That's correct. And then we've also got, that one probably should have come first. Maybe not. Should have come before this one. You don't use this one quite so often. But the other one that we need to know is the velocity at time t is equal to the velocity at 0, and the initial velocity, the velocity at time 0, plus a naught times t, where this is acceleration. And for all of these things, these are only true when the acceleration is constant, so it's not changing for a given stage. It can change between stages, but for a given stage where these equations are going to apply, your acceleration at time t is just equal to a constant. So that's why you write a naught. It's just a constant number, so it may be 10 meters per second squared, and it's going to stay like that for the whole stage of this motion. So what do we mean by the stages of motion? Well, it might be that you've got a little object, say it's a pool ball, similar thing. So it might be, so last time we kind of ignored friction, but you'd find that that little pool ball might be moving along, and it would be slowing down somewhat as it travels along. And so that would be, it would have some acceleration there. And then it's going to bounce and it's going to head in the other direction. It's still going to be slowing down as it moves along, and then it might come to a stop like that. And so there you're going to have two stages. This is decelerating. It's moving along, it's decelerating, and then it completely changes direction. And then it might still be decelerating. It might lose a bit of velocity. And there's also a third stage. And here, that bounce is going to have some accelerations associated with it. So there'll be different stages to that motion. Another example might be, you might have a car, like so. So it might initially be traveling at constant velocity, moving along at constant velocity, and then it might see some traffic lights. So there might be some traffic lights here. And so that car might be moving along with constant velocity, and then the lights turn red. Where's the red? Top or bottom? Maybe at the top. Just change that back to black. And so it might be traveling along with constant velocity, then it sees the light, so it slows down. So that would be a second stage. And then it might be at that point, the lights turn green. So the lights then turn green, and so then, oops, that car would start speeding up again and go past those lights. There would be three stages. So traveling along at constant velocity, then it sees the red light. So let me just make it go a bit quicker to start with. Traveling at constant velocity, sees the red light and starts to slow down. But then the lights turn green again, so it accelerates again, and then there might even be a fourth stage where it continues on at constant velocity. But within each of those stages, these formulas will apply. But to go from one stage to the next, you need to find the values at the end of that stage, get some new equations for the next stage to figure out things, where things are going to be and what's going to happen in that next stage. So first of all, we'll just look at a few problems that just involve one stage of motion. And so they're just going to be one set of equations, and then we'll look at a few problems that involve more than one stage of motion. Okay, so the first question, what's it asking us? So escape Earth's gravitational field, a rocket must achieve an escape velocity of 11.2 kilometers per second, which is awfully fast. I think the speed of a bullet's around 300 odd meters per second. Let's just Google it and find out. Always feet. Yeah, so somewhere between 180 and 1500 meters per second. I think usually it's around 360 odd. Maybe that's the speed of sound I'm thinking of. It is. So the speed of sound is about 343 meters per second. So the speed of a bullet's going to be a fair bit faster than that, usually. Anyway, let's get back to this problem. So it's got an acceleration of 2g, so we're going to have to figure that out what that is in meters per second. So often accelerations are given in g's, so it's equivalent to the gravitational acceleration times 2. And that can be translated back into experience. If you're traveling at 2g, it'll feel like your weight in the opposite direction is going to be 2 times the weight due to gravity. But anyway, we want to find the speed of the rocket after 5 seconds, how far it's travelled after 5 seconds, how far from the Earth the rocket will be when it reaches escape velocity, and how many minutes after takeoff the rocket will reach escape velocity. So let's have a go at each of those. So what we need to do is we need to figure out what we know first. And so the rocket starts from rest. And so let's start with A. This might not even be A, this is just general information. So what we know first is that V0, so the initial acceleration, is equal to 0 meters per second. And so all these V0s are just going to be 0. Then what else do we know? We know we're going to take our displacement relative to where the rocket starts from. So we'll also have S0 is equal to 0 meters. So we're just going to assume that where it starts from is 0 displacement. And we want to know, what else do we want to do? Oh, and we know the escape velocity, VE, is equal to 11.2 kilometers per second. And let's get everything in meters per second. So that's 11200 meters per second. I think that's all the information we've got. Oh, and we know the acceleration. So A0 is equal to 2 times the gravitational acceleration, which is 2 times 9.81, which is equal to 19.62 meters per second, or meters per second squared. So that's how much it's accelerating. Let's just double check that. 2 times 9.81, yep, 19.62. So the first thing we want to know is what's the speed of the rocket after 5 seconds. So we know A0, we know V0, we're given the time, so we want to use this equation here. So you're just looking for what it's asking for, look at what you're trying to find out. We're trying to find out the velocity at a given time, so therefore we want to be using that equation there. So let's go. So now we're on to A. So we know that the velocity at time t for constant acceleration is just given by the initial velocity plus the acceleration times the time, which is equal to, in our case, 0 plus A0. So the acceleration is 19.62 times 5, which is going to be equal to 19.62 times 5 is 98.1 meters per second is speed after 5 seconds. So it's already going pretty fast. It's a few hundred kilometers an hour, I think. So I think 30 meters per second is something like 100 kilometers per hour, roughly, very roughly speaking. So that's the first one. How far has the rocket traveled after 5 seconds? Now, there is a couple of ways we could do this. We now know the speed at 5 seconds here. We know the initial speed, we know the acceleration, and we could use this to figure out the distance, this equation here, because we know S0 equals 0, so we're just figuring out the distance. We'd have to rearrange things and figure it out. So we could use that equation, but it's going to be easier just to use this one. We know we're given, we want to find the distance at 5 seconds, and so we know S0, we know V0. The initial velocities, these are both 0, and so we're just going to use, and we know the acceleration, the constant acceleration for this motion, just A0. So we can just use that equation. So B, so the displacement at a time t is just given by the initial displacement plus the initial velocity times time plus a half times the constant acceleration times time. S0 and V0 are 0, so that's just going to be a half times 19.62 times, half AT squared, excuse me. Half AT squared, let me just go and, yeah, that should be fine. Half AT squared is what that should be. So it's half times 19.62 times 5 squared. I just want to check that I've got it right on the notes. Yep. And so therefore the distance it's going to have travelled is 0.5 times 19.62 times 5 squared, which is 245.25 metres. Is distance travelled, which is the same as the displacement in this particular case. Is the distance travelled after 5 seconds. I don't really need to write seconds in full, do I? After 5 seconds. After 5 seconds. Underline it. Now, what's it asking next? So these ones you're really just substituting into the equation. For the next one we might have to solve an equation. So how far from the Earth will the rocket be when it reaches escape velocity? So what we're going to figure out, this is an interesting one. I've written this as v at time t, but it's not really, because this is a function of s. So this is really the velocity at distance s. This is also, it's a velocity squared at distance s, because that's what we've got here. We don't have time over here. That's kind of the whole point in this. This equation tells you the velocity at a given distance when there's constant velocity. And so it's really figuring out the velocity at a certain distance. And what do we try to figure out again? How far from the Earth will the rocket be when it reaches escape velocity? And so that is probably the one we want to use. So we are going to have the velocity because we know the escape velocity that we need to get to. So we're going to have the velocity. We know the initial velocity is just 0. And we know the acceleration, and we're trying to find the distance. Now, could we have used this one up here? So we can't use this one, because this equation, at no point does it have this final velocity. So, but we could maybe calculate this first, then we've got some kind of equation with a t equals something or other, and then substitute that into here. But what you'll find is it's just this equation here. And so basically for this problem here, we're trying to figure out a distance when it reaches a certain velocity. So that means we want to use this equation that relates the velocity to the distance. So we're going to use that one there. So we're going to use c. So we've got the velocity at a given distance squared is just equal to the initial velocity squared plus 2 times the constant acceleration times distance take away initial distance. So therefore we're going to have, we know that what the velocity we're trying to get to is 11.2 kilometers per second. And so we want to know at what distance is the velocity going to be 11,200 meters per second. This is just equal to 0 because v0 was 0. So it's going to be equal to 2 times the acceleration was 2g, 19.62 meters per second squared, times distance minus the initial displacement. We're just assuming ground level is just 0. And so therefore that distance is going to be 11,200 divided by 2 times 19.62, which is just equal to 11,200 divided by 2 divided by 19.62 is equal to 280. Really? 285 meters. We'll check it in a minute. Oh, you fool. Let's go back. Sorry, I'm very foolish. This was squared. I knew that didn't look right. And so we have to square this velocity that we're trying to find the distance where that velocity is. And so S is going to be 11,200 squared divided by 2 times 19.62, which is equal to 11,200 squared divided by 2 divided by 19.62, which is going to be a big number. It's going to be 3196738 meters. So that is going to be 3,100, and so I'm just changing this to kilometers now. So I'd be bringing a decimal place 1, 2, 3 positions in. So you could actually say 3,200 kilometers from Earth is where it's going to reach that escape velocity. Cool. D. In fact, this problem is more complicated than this. I'm oversimplifying it. This idea that it's really that velocity, the escape velocity, will change, I think, as you get a bit further away from Earth. But just interesting puzzle rather than being particularly physically accurate. What was it asking next? D. How many minutes after takeoff will the rocket reach escape velocity? And so in this case, we're looking for how the length of time it'll take to reach that escape velocity. So let's double check that. So we've got this equation here will do the job this time. We're going to know the velocity we're trying to get to, and we are trying to find the time, and we know the acceleration. We know v0 0, so we can use this equation here. So therefore, we'll use the equation, the velocity at time t is equal to the initial velocity plus the acceleration times time. So we are going to have to get 1,200 meters per second. It's going to be equal to 0 plus 19 point, what was it? 82? 19 point, why did I put 19.62? Ah, it is 19.62, that's why. So 19.62 times t. So that means just divide both sides by 19.62. T is going to be equal to 1,200 divided by 19.62, which is equal to 571 seconds. And did it ask us for how many minutes after takeoff? So, which is approximately equal to, well, let's just do equal to. So we'll just divide that by 60 to get the number of minutes, which is equal to 9.51 minutes. Remember, that's not 9 minutes and 51 seconds, it's 9.51, so it's like almost, it's about a half a minute more than 9, so it's about 9 minutes 30 seconds, something like that. So what have we actually calculated here? After takeoff, rocket will reach escape velocity. And same here, 3,200 kilometers from Earth, rocket will reach escape velocity. Just underline those. Now, try to find a way to do a check here. So let's just see if we can figure out, what can we do? We could figure out, so we know these two things. This is the same thing. It's the distance at which it reaches this velocity, and it's the time at which it reaches this velocity. So what we could check is what is the distance at this time, and it should give us this distance here. So let's have a go at that. So check. And so we've got the equation. The distance at a given time is equal to the initial, or displacement at a given time is initial displacement plus the initial velocity times the time plus a half, excuse me, times the acceleration times time, which is equal to initial displacement 0, initial velocity 0, so it's going to be a half times 19.62 times 571 seconds, which is equal to half AT squared. How many times am I going to forget that? So it's 0.5 times 19.62 times 571 squared, which is equal to 3.1. Oops, I'm doing it in black. So that's going to be, and it comes out to be the same. It's 319.8426.462, sorry, which is approximately equal to 3,200 kilometers. Yep, which is what we got previously. So we're just chucking our results back into one of the other equations and just checking that result. And it looks okay. Next problem.